All right. So let's do 2.5, solve linear inequalities. Linear inequalities in one variable. We're going to start with this. We may not realize that we have used inequalities as much as we do in our daily, everyday lives. So what is an inequality? Inequalities are things or objects that are not equal. Inequalities are things or objects that are not equal. Okay? When we talk about inequalities, we're comparing objects in order to make a decision. So, for example, if I'm going to the grocery store, so what we're doing is we are comparing objects in order to make a decision. Okay, so for example, if I'm going to the grocery store and I want some honey nut Cheerios, I have options, right? I can go for the name brand or with the off-brand honey nut scooters. One thing that I can compare is the prices. So for example, honey nut Cheerios, is $4.29, and the honey nut scooters is what? $2.89. If I only care about the price, I will go with what? With honey nut scooters, right? So in this situation, I have made a decision based on comparison of prices. And in math, this represents an inequality. So let's do price of scooters and the price of Cheerios. It's less light, right? So the money remaining here after buying the scooters is more than the money after buying the scooters is going to be what? I'm going to have more money than if I go and buy the Cheerios, right? Now, I don't always base my decisions on just one input, like in this case, the price. We have another inputs like what about brand loyalty or the need for quality, which sometimes it confuses us with the brand, the name brand objects. So we could say oftentimes we have situations where we will have to judge multiple inequalities and then make a decision. In math, we always try to boil down the situation to numbers. So this will become problems like, for example, price of object 1 is more than the price of object 2, right? And or quality of object 1 is less than quality of object 2. We will talk about this when we get to the intersections and the unions. Don't worry about it, okay? The price of the object is more, and we don't know if the same one, the quality of that object is going to be less than the other one. So let me give you another example. Suppose we're buying a new phone, okay? And we looked at our account and we noticed that we can only afford a phone that costs less than $500. So how can we represent this in an inequality? So we're gonna say it less than 500, right? Where X is the price of the phone, which right now is unknown because I don't know how much. So this example is based on suppose we're buying a new phone and you can only afford less than 500. So that's how we will write it. So now, how many solutions could we purchase that fit this model? How many solutions, meaning how many type of phones could we purchase that fit this model? The model meaning less than 500. Theoretically and realistically, are two answers, two different answers. And let's do the first one. Realistically, all available phones that are less than 500, right? Less than 500, all of them. This is a countable, let me write it down. This is a countable number of phones. Now, theoretically, there are infinitely many phones we could purchase. Many phones we could purchase. Okay. In theory, we could pay what? 499.1234.009, right? For a phone. Or we can pay 499.00000878. But in reality, we don't. Okay? So the point is that there is not just one solution for linear inequalities. There are infinitely many solutions. So it's going to be all of the numbers that are less than 500. Let me write that down. The point is there is not just one solution for linear inequalities, okay? There are infinitely many solutions. All numbers that are less than 500, all numbers less than what? That 500 will qualify for that, okay? Now, let me just adjust this, okay. So let's do the inequality symbols. Let's go over that first. So if we go back to our example where it said X needs to be less than 500, the phone that I'm gonna buy, what number that fits this solution is negative 10. But will we ever pay less a negative 10 for a phone? What will that mean? That the cell company is gonna give me, the cell phone company is gonna give us the phone and pay us $10 to take it? So that's not realistic. But we still want to write an inequality that makes sense to us. So let's write an inequality that takes this into account. So we'll say we're going to buy a phone that cost us some money. So it's going to be greater than 0 and less than 500. Okay? Again, negative 10 can go here, but it's not going to make any sense because they're not going to give me, the cell phone company is not going to give us a phone plus $10. So we need to write an inequality to take that into account. That we want to write something that it makes sense to us. And this is an example of what we call a compound inequality. So this is an example of a compound inequality. Okay? We have added upon our original problem. So that's what we say we have compounded. So we have added upon our original problem. So we have compounded, okay, it. So what we really have there is two inequalities in a single statement. We really have two inequalities in a single statement. So we're going to be dealing with what? With single inequalities, like x less than 500, and compound inequalities, which is where greater less than 5 and greater than 0. All right. Now, there are 4 basic inequality symbols. 4 basic inequality symbols. Let's go over those. Okay. The first one. This one means is greater than. Is greater than. Now, this one is greater than or equal to. Remember the difference. Is greater than is this one. When it has the line here, is greater than or equal to. Now, this one is less than. This is less than. And, oh, let me use a different color. And this one is less than or equal to. Okay? So, this is less than is not the same as, it's not the same as less than symbol, as less than means to subtract. And we can use the, hold on. This is what we need to make sure. You see, is all of them. Each of these have a different solution set. And we say set because their solutions are infinite. There are infinitely many different solutions to each of these inequalities. And let me write that down. Each of these have a different solution set, okay? And we say set because their solutions are infinite. Infinite solutions, okay? So there are infinitely solutions, many different solutions. There are infinitely many solutions to each of these inequalities. Okay? Now, what's the difference between what's the difference between means that what? That x greater or equal to 4, what happens? Includes 4. This is true. And x greater than 4 does not include what? Does not include 4. So then we cannot say 4 greater than 4. This is not true. Okay? So let's look at some at the graphical representation using pictures. And we're going to use a number line. And let me just do that here. Note that our number line does not have to include that does not have to include 0. So I'm only going to include the number that were given or found on the number line. So let's do this. What does x greater than 4 looks like? So here's the number line, and here's the number 4. Means that what? All of the numbers on this side. So we're going to color all the numbers larger than 4. So do we include the 4? So we have two ways to graphically show that we're not including the 4. We either going to be using an open circle. Hold on. Let me write it down here. Okay, so there are two ways that we could do this. You could just use an open circle, which means you're not including the 4, or open parentheses. I like the open parentheses a lot. That's the one that I use all the time. So there are two ways to graphically show that we do not include the number 4. Open circle or parentheses. And let's do the other one. Right here, what do we do? Again, it's going to be two ways that we can so we have two ways to denote or to graphically to include the number 4. We either do it with a circle, color it, or with a square, with a square bracket. That's going to point to our coloring area. So either this one or this one. Again, I use the open parenthesis when the number is not included, and when it's included, I use the bracket. Okay? Now, let's keep going. We are going to do the part that says flipping the inequality sign. So when we have inequalities, like suppose we are dealing with x equal to 4. So when we have like x equals to 4, we can rewrite as what? 4 equals to x, right? And we can do it because there's no difference in saying our number is 4 or 4 is our number. However, when we use inequalities, we cannot do this so easily because there's a difference between, when we're doing inequalities, there's a difference between saying x greater than 4 and if we were going to switch the number like we did. Okay, it's not the same. So we have seen greater than 4, which is this one, right? This is the graph. Now, let's graph this one. Okay? So hold on. So we're gonna graph of 4, and what do we have? So it's going to be all of the numbers that are what? Less than 4. So 4 is larger. So how do we say it? We said 4 is larger than all other numbers. So this means that 4 is the biggest number. Okay, so our solution set is all numbers smaller than 4, right? So all numbers smaller than 4. And if we were going to rewrite it, so we said 4, this is what we have, right? So we do x less than 4. Another thing that you could do, notice that the inequality symbol flips along with the numbers when we rewrite them. Let me write that down. Notice flips, okay, along with the numbers. With the numbers when we rewrite them, okay? Another way to see it is I just look through this x less than 4. So all of the numbers that are less than 4, looking from this side, not from here, from this way, this way. Now, the next one is says more flipping. Let's see, what else do we have? More flipping. So we heard about the rule that says when you multiply or divide by a negative number, you flip or change the inequality symbol. So do we know why that really happens? Why are we really doing that? So let me see. Suppose we have so I'm going to write it down here. When you multiply or divide by a negative number, what do? You flip or change the inequality symbol. And I'll show you why we do that. Why is that true? So let me give you an example. It says, suppose we have the statement so we have a statement that says that negative x is greater than 3. So let's think about the solution to this without actually solving it. So let's look at the graph. We have 3. What numbers make this statement true? So if a number makes the statement true, we will color it in the graph. We will color it on the graph. So for example, let's say a number, 2. So let's say I said x is equal to 2. So we're going to check to see if it's true or not. So we're going to create a solution set this way by figuring out which numbers work for us and which ones do not work. Okay? And let me see exactly what we did here. So 2, negative 2. So for example, 2, that's 2. What happens if I write down here 2? So negative 2 is greater than 3? No. No, right? That's what we have to flip the, this is why when we divide or when we multiply by a negative number, we flip or change the direction of the inequality. Because, for example, and I'm going to give you another number. For example, we have, let me just do this. I'm multiplying by negative 1 on both sides of the equation. Okay? Right? I take back this part that I just said. Okay? Take this back. Erase that from your brains, guys. So what do I get here? I get x. And what happened? I just multiplied by negative 1. So I flip the sign. And it's going to be x less than negative 3. So this is the same as x less than negative 3. Because when I multiplied or divide by a negative number, we flip the inequality symbol. We have to do it in order to make this true. When we multiplied, what did I do? I flip the symbol. So then this is the same as this. Okay? And the last part of 2.5. Now we're going to be talking about notation. What are the different ways that we can write inequalities? So suppose we consider numbers larger than 5 or 5x greater than. Let me write this down. So suppose we consider numbers larger than 5, or we said x greater than 5. Okay, so there are two ways we can write this. There are two ways. One way, we already talked about it. So It says set builder notation. What do we say here? That describes the set but does not include the list of the elements. Describes the set but does not list the elements. Now, for example, the set of numbers, for example, this. That's the set builder notation. And it means that the set of all numbers such that the numbers are greater than 5. That's how you read it. The set of numbers. This line here means such that what? The numbers are greater than 5. Okay? However, we typically assume that the numbers are real numbers too. So we don't really have to, because this is another way that we could do it. We want to be more specifically. Although the set of numbers such as that all those numbers are elements of the real numbers. So we typically assume that the numbers are real until we are told otherwise, okay? Now, let's do the next one. This is the one that we haven't done, the interval notation. Okay, so the interval notation tells us the boundaries of the numbers. The boundaries of the numbers. Okay, and this is how we write it down. We do lower bound and upper bound. Okay, or remember brackets, no? Open parenthesis, or when it's included, we're gonna use the bracket, upper. Okay, this one, like we said, is to the boundary numbers. Okay, and this one includes. Okay, so how will we write down x greater? We could do it there. We still have space. So how we're gonna write down how? You know what? Let's turn the page. So how will we write x greater than 5 using interval notation. So we need to see, okay, is 5 a lower bound number or an upper bound number? So let's use the graph. So we have the number 5, okay? And it's going to be open this way, right? Now, the interval is here, right? So we're going to have open, what is going to be the lower bound? It's going to be 5. And the upper bound is going to be infinity. Okay? Now, you need to remember infinity is never going to be a closed, for example, no, never going to be closed, always going to be open. Okay? Open parentheses for infinity. For infinity is open parentheses. Don't forget that, okay? And that's it for 2.5.